Welcome to Mathematical Physics. Today, we are going to explore a brilliant mathematical tool called the integrating factor. If you have ever felt stuck trying to solve a differential equation because the variables just will not separate, you are in the right place. This technique is like finding the perfect key to unlock a stubborn door. By the end of this video, you will understand exactly how to use this magic multiplier to solve complex equations in physics, from cooling coffee to electrical circuits. Let us dive in. To begin our journey, imagine you are trying to solve a complex puzzle where the pieces just do not seem to fit together, no matter how hard you try. In the world of differential equations, we often encounter equations that are just as stubborn. They refuse to be solved using basic methods like separating the variables. We call these inexact equations. In physics, these pop up everywhere, describing systems that are changing in complicated ways. We cannot just integrate both sides directly because the math does not line up. We need a way to force the equation into a shape that we know how to handle. This is where our special tool comes into play. Now that we understand the problem of stubborn equations, let us look at the solution. Imagine someone hands you a special pair of glasses that suddenly makes the edges of those puzzle pieces change shape so they lock together perfectly. The integrating factor is exactly like those special glasses. It is a magical mathematical multiplier. When you apply it to the entire stubborn equation, it instantly transforms it into a perfect, easily solvable form. By simply multiplying everything by this specific function, the messy left side of our equation collapses into a neat, tidy derivative. This clever trick relies on the product rule from calculus, turning an impossible integration into a straightforward one. Before we can find our magic multiplier, we must ensure our differential equation is organized properly. This brings us to the standard form. You must arrange your equation exactly like this, or the formula will give you the wrong answer. The symbol y represents the unknown function we are trying to find, and x is our independent variable, like time or distance. The function p of x represents whatever is multiplying our y variable. Finally, q of x is the function on the right side, representing an external force or input to our system. Notice that the coefficient in front of the derivative must be exactly 1. If there is a number there, you must divide the whole equation by it first. Now that our equation is in standard form, we can calculate the integrating factor itself. This formula comes from forcing the left side of our equation to look exactly like the result of the product rule. Here, IF stands for the integrating factor. The symbol E is Euler's number, which naturally appears in growth and decay processes. The exponent tells us we must take the function p of x from our standard form and integrate it with respect to x. We usually ignore the constant of integration during this specific step because it would eventually cancel out anyway. If p of x increases, the integrating factor grows exponentially, which perfectly counterbalances the terms in our original equation to make it exact. Once we have our integrating factor, we multiply the entire standard form equation by it. This leads us to our ultimate goal, the general solution formula. Conceptually, the left side has collapsed into the derivative of y times the integrating factor. When we integrate both sides, the derivative disappears, leaving just y times the integrating factor on the left. On the right side, we take the original right-hand function q of x, multiply it by the integrating factor, and integrate that entire product. The symbol c is the crucial constant of integration that arises here, representing the initial conditions of our physical system. To find the explicit solution for y, you simply evaluate the integral on the right and divide by the integrating factor. Let us put this method into practice with a straightforward mathematical example. We are given a differential equation and asked to find the general solution for y. We cannot solve this by simply moving all the x terms to one side, so we must use an integrating factor. First, we verify the equation is in standard form. The coefficient of the derivative is already 1, so we are good to go. We identify p of x as 2 over x and q of x as x squared. We substitute p of x into our integrating factor formula. The integral of 2 over x is 2 times the natural log of x. Using logarithm rules, we move the 2 inside as an exponent. Because the exponential and natural log are inverse functions, they cancel perfectly, leaving us with a beautifully simple integrating factor of x squared. Now that we have our integrating factor, let us finish solving the equation. We use our general solution formula, multiplying our unknown y by the integrating factor x squared on the left. On the right, we multiply our original q of x, which was x squared, by our integrating factor x squared. This gives us x to the power of 4 inside the integral. We also add our constant of integration c. The integral of x to the 4th is simply x to the 5th divided by 5, according to the power rule. To find the explicit solution for y, we isolate it by dividing every single term in the equation by x squared. This gives us our final general solution. The first term represents behavior driven by the input, while the second term represents transient behavior depending on initial conditions. We have just successfully used the formula, but as physicists, we must understand why it works. Let us look at the mathematical reasoning behind this method. We start with our standard form equation. Our goal is to force the left side to look like the expanded form of the product rule from calculus. We do this by multiplying every single term by our integrating factor. Now, look closely at the left side of the equation. It has 2 terms, just like the product rule expansion, which states that the derivative of u times v equals u times the derivative of v plus v times the derivative of u. We want our left side to perfectly match this pattern, where our unknown function y acts as one of the variables. Continuing our derivation, because of how we carefully defined the integrating factor using that exponential formula, the left side perfectly collapses. It becomes the exact derivative of the product of our unknown function y and the integrating factor itself. This is the magic step. We have transformed a messy addition of terms into a single, clean derivative. To undo this derivative and solve for y, we simply integrate both sides with respect to x. The integral of a derivative just gives us the original function back, leaving y times the integrating factor on the left. On the right, we are left with the integral of q of x times the integrating factor, plus our constant c. This proves exactly where our general solution formula comes from. So, we have proven that the math works perfectly. This brings us to why we care about this in physics. You might be wondering why we go through the trouble of finding this multiplier instead of just using computers to guess the answer. The truth is, the integrating factor is the backbone of modeling countless dynamic systems in physics and engineering. Without it, we could not easily find exact analytical solutions to real-world problems. For example, it is used to calculate how a cup of coffee cools down over time according to Newton's law of cooling. It is also absolutely essential in electrical engineering for analyzing circuits, where the current changes over time based on supplied voltage. It bridges the gap between setting up a physical law and getting a usable formula. Before we move on, let us see this with a concrete physics example. Imagine an electrical circuit containing a resistor and an inductor connected to a battery. According to Kirchhoff's voltage law, the current I is governed by this differential equation. We want to find how the current changes over time t. Notice that the derivative has a coefficient of L. To use our formulas, we must first force the equation into standard form by dividing every term by L. Now, our independent variable is time t and our dependent variable is current I. We identify P of t as the constant R over L and Q of t as V over L. Since R over L is a constant, its integral is simply R over L times t. This gives us an exponential growth function for our integrating factor. Now we plug our integrating factor into the general solution formula to find the current. On the left, we have our unknown current I multiplied by the integrating factor. On the right, we integrate the product of our Q of t term and the integrating factor. Because V over L is a constant, we pull it out of the integral. When we integrate the exponential, we must divide by the constant in the exponent, which means multiplying by L over R. The L's cancel out beautifully. Finally, to isolate the current I, we divide the entire equation by the integrating factor. This final equation tells us exactly how the current behaves. The first term is the steady-state current, and the second term is the transient current, which decays to zero over time. Now that we have solved a real-world problem, let us visualize the entire process we just learned. This flowchart summarizes the integrating factor method perfectly. At the top, we start with our inexact ordinary differential equation in standard form. The first major step, shown by the downward arrow, is to calculate and multiply by our custom integrating factor. This forces the equation into the middle box, where the left side has collapsed into a simple exact derivative using the product rule. Finally, the last arrow shows us integrating both sides to arrive at the bottom box, which is our final general solution. This diagram represents the fundamental path we take to solve problems involving continuous change. We have covered a lot of ground today, so let us review the most important ideas. First, always remember that your differential equation must be in standard form before you do anything else. The coefficient of the derivative must be 1. Second, the integrating factor formula is your magic key. It is e raised to the integral of p of x. Third, multiplying by this factor transforms a difficult non-integrable equation into a simple exact derivative via the product rule. Finally, this is not just an abstract math trick. It is a powerful tool that unlocks exact solutions for real physical systems, from fluid dynamics to electrical circuits. You now have the power to solve these complex equations. Great job today.